SwayamPrabha. Digital India. Educated India.
Hello everyone. Today I am going to deliver a lecture on welded joint static analysis related to eccentrically loaded welded joint. So, last class already I have discussed about the theoretical portion of eccentrically loaded welded joint. So, from there what we observed that in case of eccentrically loaded welded joint, there generally occurs two different types of shear stress. One is called primary shear stress, another one is called secondary shear stress. So, depending on this primary and secondary shear stress, we have to design generally the welding dimension. Welding dimension in the sense like weld throat thickness and its leg length. So, the detailed step already I have discussed in last lecture. Today I will solve some problem on that topics. So, this is the content of today's lecture, that means we will solve some problem on analysis of eccentrically loaded welded joint. The first problem which I am showing here, the problem statement is like a welded connection. Here you can see this is the weld connection which is shown in this figure is subjected to an eccentric force of 7.1 kilonewton. So, here the given parameters are the externally eccentric load P equal to 7.5 kilonewton, 5 kilonewton. So, here we have to determine the size of the weld. So, we have to determine the size of the weld means, so here size of the weld, what does it means? I have already discussed. Size of the weld means we have to find throat thickness, and leg length. So, these are the things we have to find out. So, what are the things given? The permissible shear stress of weld material, you can say, or of the weld is 100 MPa. So, here the given another parameter is tau p, that is permissible shear stress of the weld material is 100 MPa. Okay. So, based on this two parameter and from this figure, joint geometry, or we can say length of the weld, we have to find out what? We have to find out the throat thickness, that is T, and leg length H. These two things we have to find out. So, last lecture actually I have discussed about how to find this throat thickness and leg length theoretical portion. Today I will just solve one problem, then it will be very clear to you. So, what are the things we have given here? The given parameter is eccentric load P and permissible shear stress tau P, and weld length also is given here. That means, and the detailed figure which is representing the connection of bracket with another plate, you can say. Okay. So, step by step now I will solve this problem, then it will be very clear to you. So, first step is to find out the primary shear stress, because we know there are two different shear stress which is acting in this case of problem. One is called primary shear stress. So, how to find out this primary shear stress? First of all, I will discuss here. I am representing, this is a step 1, this is a step 1. So, we know this primary shear stress is represented in tau 1, which is equal to external load P divided by total cross sectional area. Because we know that the last lecture already I have discussed this eccentric force we can transmit from this external position O to CG of this weld. So, CG of this weld G. So, once we shift this load from this external position O to CG of this weld. So, in this location generally here you can see, as this is two symmetric weld, this is weld 1 and weld 2, and its G will be at the mid length of this two weld, you can say. So, if this is the length of the weld is L. So, if we consider from this side, so this distance will be L by 2. Okay. Now, we can easily find out what is the eccentric distance E. So, eccentric distance E here will be due to symmetric weld, eccentric distance E will be your 100 plus L by 2, that is your 100 plus L by 2 here, nearly 50 by 2, that will be your 125. Okay. This is the eccentric distance E in between what it is called G and O. So, eccentric distance E here you can say G O is equal to this. Now, we are shifting this load, this P is equal to your 7.5 kilonewton from this O to G. So, in this G there will generally act a similar force P, because according to principle of applied mechanics we know these things, and there will be a moment, or you can say couple M. This couple M should be equal to your load, that means this externally applied load P, and the distance between this G and O, perpendicular distance between G and O is E. So, couple P. So, due to this load P, last lecture already I have discussed, due to this load P in the weld there will act a uniformly distributed, you can say, shear stress, that is called primary shear stress, whose direction generally opposite to the direction of what? Direction of applied force, externally applied force P, okay, because here this externally applied force P is downward. So, here this whatever the resisting shear stress developed inside weld due to this direct force P. So, this will be just opposite to the direction of that applied load. This you should keep it in mind, because what happens, we know that whatever the stress developed inside a material, that is opposite, that is developed due to the resisting of effect of applied force. So, resisting effect force direction will be opposite to the direction of applied force, that is why resisting stress direction also will be opposite to the direction of applied force. So, this is called tau 1 stress, or you call this is called primary shear stress. So, for finding out primary shear stress, what are the things required? In primary shear stress we assume that the shear stress is uniformly distributed over the throat cross sectional area. So, let us consider here, the throat thickness of the weld equal to T. So, what we want to find out actually T and leg length H. So, let us consider this throat thickness of the weld is T. So, what should be the total area of the weld? Here you can see two symmetric weld are there whose length is also equal. So, the total area in the plane of throat thickness will be your T into L, two welds, two similar weld symmetric weld you can say. So, it will be your 2 into T into L. Okay. So, this total throat cross sectional area we can get as 2 into here throat thickness T and L is 50. So, we can write as 100 T is let the dimension I am consider in terms of millimeter. So, it will be millimeter square. Now, here P applied force is given as 7.5 kilonewton. 7.5 kilonewton. So, your tau 1 here the primary shear stress tau 1 will be your 7.5, this I am converting in terms of Newton to 1000 divided by cross sectional area is 100 T. So, this will be equal to you can write at 75 divided by T Newton per millimeter, because this is a stress. A stress means load per unit cross sectional area, you can say load per cross sectional area, that is why Newton per millimeter square its unit. So, this is the first step. So, in first step we already find out what is tau 1. Now, due to this moment M, due to this moment or you can say couple M, there will develop a secondary shear stress, there will develop secondary shear stress. So, there is a couple M. So, now we have to find out secondary shear stress. So, this secondary shear stress, so step 2 here I am writing step 2, we will find what is secondary shear stress. So, this is the step to find out secondary shear stress. So, secondary shear stress is tau 2. So, tau 2 generally we know this formula for tau 2 is equal to your M R by J. So, this thing is very well known to you, I have already discussed in last lecture. So, from here what we observe that this tau 2 is proportional to radial distance r, here you can see radial distance r. So, this is the G. So, about G generally the maximum secondary shear stress, because the primary shear stress is uniform throughout the entire weld length, but this tau 2 secondary shear stress is depends on distance from CG to weld length different points. So, here you can see because it is generally depends on distance from CG to the position of weld line different points. So, here you can see because here from here to here, if you just consider this r, if we consider from here to here this r, then here you will get one types of tau 2. So, let this is tau 2 1, I am just considering. If you consider this point, here this r will be different, here the r will be different. So, here one r you will get first case. So, here also you will get another r. So, let this is your tau 2, tau 2 2, let us I am representing. So, here you can see M and J, this is constant you can say for a particular set of weld joint, but here this R is generally varying from this G, which is generally proportional to the radial distance you can say, or distance from different point of this weld, different point of this weld from the location G, where G is what? G is the overall CG of all welds. This also you should keep it in mind. So, here G is what? G is the CG of wall welds, this you should keep it in mind. So, here we have to consider G as CG of welds, not CG of plate, because here we are finding out the stress distribution inside the weld. That is why here we have to consider the CG of wall weld, not the plate. Okay. So, here depending upon this r distance, this tau is varying. So, here we should consider where is the maximum secondary shear stress is acting. So, to get maximum secondary shear stress, we have to consider the location of the weld which is the farthest distance from G. So, here you can see as these two welds are symmetric and as it is the midway length you can say of this weld. So, here generally you can observe that the farthest point is any corner point of the weld, you can say any corner point of the weld you can say. So, in any corner point of the weld you can say we will get the maximum shear stress. Why? Because the distance of G to any corner point is same. So, any one of the corner point here we can consider as tau 2 maximum shear stress, okay, because here we are going to design the weld joint. That is why here we have to consider what? Here we have to consider the maximum one. But here in case of primary shear stress, we assume that it is uniformly distributed over the entire length. That means, it is uniformly distributed over the entire length of the weld. But tau 2 is depends on this r distance. So, here you can say tau 2 max we have to find out. So, tau 2 max here we have to find out this tau 2 max will be m into r maximum distance divided by J is the polar moment of inertia. So, here tau 2 max we are interested to find out. For that we have to find out what is the r max value. Okay. So, here now I will show you what is r max. So, r max generally here will be directly here I am drawing this thing, then it will be more clear to you. So, this is the G location. So, here generally tau max is the farthest distance I already told. This is the M couple. This M couple is equal to your P into E. E already I have already shown you what is E, and farthest distance this is the R max you can say, and I have already told you the direction of tau max always opposite to the direction of moment. Here you see, and the direction should be always perpendicular to the radial distance, always perpendicular to the radial distance of G to that point, that means farthest point. Let this farthest point is A, I am considering. Okay. So, this is your tau 2 max. Okay. This tau 2 max, so we have to find out what is this R max. So, R max we can easily find out. R max generally here these things is given, we can easily find out what will be the R max. So, this is 25, this is also 25. So, we know that this hypotenuse of these things will give us the R max. So, R max will be how much? So, R max will be your 25 square plus 25 square, correct. So, this will give us a value of R max is equal to your 35.36 millimeter. So, we know what is M, M also I have calculated, that is equal to your P into E. So, P is 7.5 kilonewton, it is given, into here E is 125 millimeter, which I have already shown. So, this M will give us as, here you can say 937 500 Newton millimeter, because here generally force into distance, that is why its unit is Newton millimeter. Okay. Now, tau max is known to us, the now M is known to us. Now, the another unknown here is J. So, what is J we have to find. So, for finding out J, I have already calculated last lecture that for finding out J generally what are the steps we generally follow. So, to finding out J, I have already told you J equal to J about G of any weld. Let us weld let this is weld 1. So, let us for J about G of weld 1 is equal to, I have already told you, Ixx plus Iyy plus, due to this parallel axis theorem, area of that weld 1, area of this weld 1 into distance between G to G1. G1 is the center of gravity of weld 1. That means, this only one, its center of gravity is G1. Now, here I have already last class shown, that means Ixx, here I have already shown that this is actually L TQ by 12 plus, because this Jg we are finding out the cross sectional area in throat, okay, in throat region. So, Iyy equal to, we know, TLQ divided by 12 plus A1 into Gg1, here as it is generally mid length. So, here Gg1 is 50 by 2. So, here generally Gg1 distance is 50 by 2 millimeter. Now, compared to L, here L is much greater than this T, you can say. That is why this first term I have already told you in last lecture, we neglected, we consider as equal to 0. So, we can get that this Jg1 equal to your T into L into L square by 12 plus A1 into, sorry, this G1 square, this will be G1 square. So, this distance is equal to your, let us this distance from Gg1, then let this distance from Gg1 I am representing in terms of R1. Okay. So, this will be your R1 square. So, this we can write as, here T into L, we know that this is your weld area, let this T into L is weld area A1 I am representing. So, A1 I am taking common, L square by 12 plus R1 square. So, everything is known to us except T. So, here we can easily find out what is Jg1, that means polar moment of inertia of weld 1 with respect to G. So, here polar moment of inertia of weld 1 with respect to G, what we can get? So, here A1 equal to T into L, L of the weld is given as 50 into L square by 12 means 50 square by 12 plus here Gg1, this distance R1 also, here you can find out L by 2, that is our 25 square. So, by this we get J1 equal to, you can say Jg1 equal to, we can say equal to your 41667 T. Now, its unit will be what? Here you can see its unit will be T into LQ, means 4 power of length. So, here it will be millimeter to the power 4. Now, two symmetric this weld are there. So, this upper side one similar weld and lower side another similar weld, and the distance between this lower side weld, that means weld G2, this distance also is 25. So, what happens, the polar moment of inertia of Jg2 also will be same as Jg1, because both are symmetric, which is also equal to your 41667 T millimeter to the power 4. So, here the total polar moment of inertia. So, here total, we are writing total polar moment of inertia of wall weld, here whatever the welds are there. So, is let Jg. So, this Jg will be equal to your Jg of weld 1 plus Jg of weld 2, this you should keep it in mind. So, this will be equal to 2 into 41667 T. So, this will be equal to we can say 83334 T millimeter to the power 4. Now, we know Jg, then m and R max. So, we can easily find out what is tau 2 max. So, tau 2 max will be equal to our m into R divided by J G. Okay. So, here m is given. So, m is given as 937,500. This into R, R is the farthest distance, you can write as R max. Okay. So, here R max is what? So, R max is 35.36 millimeter, we have already calculated, and Jg is the polar moment of inertia of all weld, which is equal to 3334 T. So, what is the tau 2 max we are getting here? Directly I am writing, this will give us 397.397.8 divided by T, and its unit will be your Newton per mm square. This you should keep it in mind. So, we got tau 2 max and what it is called? Tau 1. Now, tau 1 we know and tau 2 max also is known to us. This 2 value is known to us. Now, based on these things, we have to find out what is the resultant shear stress at that farthest point. Okay. So, this resultant shear stress at this farthest point should not exceed the permissible shear stress. Okay. Then these things generally we have to compare, from there we can easily find out what is T. So, now we have to find out the resultant shear stress, this is step 3. So, we have to find out resultant shear stress. So, for finding out resultant shear stress tau r, we can use here vector addition or some parallelogram law here we can use to find out this tau r. So, here at point A, let this is the point A, at point A there is a shear stress, primary shear stress tau 1, and at point A, note it down, there is a secondary shear stress, this is the secondary shear stress tau 2. Now, what is the angle between this tau 2 and horizontal shear stress, that you should know. So, angle between this tau 2 and horizontal shear stress we can easily find out from this geometry. Here you see this is 25, this is 25 and this is also 25. Now, here you see we know this tau 2 always perpendicular to the radius connecting this G and that point. This you should keep it in mind, because what happens, this generally developing due to this turning moment or torsion types of effect or couple you can say. So, this couple generally try to rotate this workpiece. Okay. So, once it try to rotate, that means in this farthest point there will develop a what it is called curve like rotational displacement, correct. So, in this farthest point in this curves, once we draw a tangent, that tangent direction represent the shear stress direction. Okay. And its direction, as it the tangent represent the shear stress direction, we know this tangent at a point always perpendicular to radius connecting that point. Okay. So, these things you just should keep it in mind. So, here we have to find out this theta angle. So, we can easily find out what is the theta angle. So, first we can find out what is this angle, So, let this angle is phi. So, this phi angle we can easily find out what is the phi angle here. So, phi angle we can easily find out tan phi we know, tan phi equal to here 25 by 25. So, here we can say phi equal to 45 degree. So, if phi equal to 45 degree, then this angle theta also here is 45 degree, you can see. So, this theta angle also is, so here you can say theta is also equal to 45 degree. Now, what I am doing here, this tau 2 max, you can say this tau 2 max I am distributing in vertical and horizontal direction. So, once I divide this tau 2 max in vertical direction, here we will get tau 2, this component will be tau 2 max, you can say sin 45 degree, and this component of this tau 2 max will be horizontal component, this will be tau 2 max cos 45 degree. This is very simple things. So, from here this we can equal to, here we will just sum this vertical tau 1 and tau 2 max component and horizontal component separately here we will draw. Then what will be the thing? So, here at point A there will be vertical shear stress component due to this primary shear plus tau 2 max sin 45 degree, and there will be another horizontal component, that is tau 2 cos 45 degree, because tau 1 do not have any horizontal component. So, from here we can easily find out what is the resultant component of this, this horizontal and vertical component, that we can easily find out, that I am going to show you. So, here tau 2 max we are getting as, already I have told you, 397.8, and tau 1 also I have shown you, that is 75 by T. Okay. So, once we sum this tau 1 and tau 2 sin 45 degree, then we can get this total vertical component as 356.3 divided by T, and this horizontal component we are getting as 281.3 by T, 281.3 by T. Now, we can easily find what is the resultant component here, as here this horizontal and vertical component of 2 stress is known to us. So, the resultant component will be, we can say this vertical I am representing, let this is our tau v and let this is our tau h, okay, horizontal component. So, here tau v square plus tau h square. So, here resultant shear stress component we are getting as 454 divided by T, its unit will be Newton per millimeter square. You can say this is the maximum resultant shear stress component due to primary and secondary shear stress on this weld. Okay. This, so now we have to find out the size of the weld. So, the fourth step is to find out the size of the weld. So, size of the weld, for finding out the size of the weld, here we have to use the criteria of principal shear stress. We know the principal shear stress is given as, this principal shear stress is given as 100 MPa. So, what is the 100 MPa? This we will convert in terms of this Newton per millimeter square. So, this will be generally 100 Newton MPa, means 1 MPa equal to 1 Newton per millimeter square. Now, for designing this welded joint, this maximum resultant shear stress, this maximum resultant shear stress in this weld should not exceed this permissible shear stress. That means, here we will equate this equation, let this is equation 1 with equation 2. So, equation 1 with equation 2, once we equate, we will write here tau r max should be equal to your tau p. So, if we just put these things, what we are getting here 454 divided by T is equal to your 100. So, here T how much we are getting? So, throat thickness T we are getting 4.54. So, here we can take the next full digit value, that is 5 mm we can say. So, the throat thickness, this is throat thickness of this weld should be 4.54, or you can say 5 millimeter, not less than 4.54. This you should keep it. If it can be little bit higher side, then we will be in more safe side. What I am telling, understand? It should not less than this 4.54. So, once we do the welding, which has a throat thickness T equal to 4.54 or more than this, then our this eccentric loaded types of a structure will be in safe side if it is subjected to 7.5 kilonewton. So, beforehand we can tell the welder whatever the welding you should do in this two weld location, this throat thickness should not less than 4.54. If it is less than this, then our things will be failed. So, if throat thickness is 4.54 or 5, then what should be the leg length? So, leg length H will be equal to your, we know this T by 707. So, here we can write 5 by 707, which is around 7 millimeter, what I am telling, understand. So, leg length. So, beforehand we can tell the welder for these types of welding connection what should be the leg length. So, by this procedure generally we can find out the design dimension of welding or welded joint you can say. So, these are the reference books which I have followed for this lecture. Thank you.